Okay, we're continuing on here. Chapter 14. Didn't get very far, I don't think, in the chapter 14, if I remember correctly. So in this chapter, as I mentioned before, this is a fairly long chapter. In most books, they will break the chapter up into kind of two separate ones. So we're going to kind of do that. As I mentioned before, we're going to kind of do part one here, which is some basic pH type stuff. And then we'll do sort of part two of it, which will cover a little bit more difficult type stuff like buffers and titrations. So we last time talked about an acid and some definitions of an acid and base, and a reminder that sort of the early definition of an acid and base is one that was done by Arrhenius. He did a lot of work with electrolytes, and again, he described an acid as basically a substance that has the ability to produce H plus ions in solution or H3O plus ions in solution. And again, a reminder that what we're talking about is the ability to really produce free floating H plus ions in solution, not attached to anything, just, by itself. A reminder that for all acids, the cation for all acids is H plus. And so that's basically the basic property of an acid is its ability to release that H plus into solution. If it's able to do that really well, it's a strong acid. If it doesn't do it so well, it's a weak acid. But it does has to have that sort of property. Now, obviously, in acid-base chemistry, a couple things that I think we might have touched upon last time, but just in case we didn't, H plus and H3O plus, which is the hydronium ion. They are all intents purposes the same thing. And in sort of acid-base chemistry, you can use H plus in formulas, equations, and so forth. You could also use H3O plus as well in equations, formulas, and stuff. Nowadays, books and stuff like to use H3O plus a lot, but I kind of still use H plus a lot. So really, anywhere I put H plus, you could substitute H3O plus basically in for it. It really represents the acidic part of the solution that's going on in there. Later, we'll also see H plus is also referred to as a proton as well, and in terms of acid-base chemistry, as you see it. So here's a strong acid, which is hydrochloric acid, dissociating over here in water. And because it's a strong acid, it's going to 100% break apart. And just to sort of illustrate, since we have this equation here, why maybe H plus is used or H3O plus is used in an equation, it really does depend on sort of how you write the equation. And for acids, for example, when they dissociate in water, which is a fancy way of saying breaking apart into ions, you can represent that two different ways in terms of an equation. You could represent it like it is here, where basically here the acid's going to send over an H plus to the water, and it's going to make H3O plus and Cl minus. And really what we see here is really just really the acid as it goes for a swim, basically breaking apart in solution. You can kind of simplify that equation, and it's done by a lot of people to simplify this equation by sort of not including the water in that part of it. And you could also write an equation where you could have the hydrochloric acid just simply breaking into H plus and Cl minus. And here I did not include water in my equation, and I just showing the H plus coming off of the acid, which is perfectly legitimate way and fine way of doing it. And if you do include the water, which sometimes people like to do with acids, that is how you're going to actually generate the H3O plus in there. So they both again represent really the H plus or the hydrogen concentration that's in that solution. And that's really why in one case you'll sometimes see H3O plus, and in some cases you'll just see H plus kind of used. And it really has to do with whether or not you kind of include the water there in the equation. A base is a substance that can produce hydroxide in solution. And when we're talking about a base, it is, again, much like the acid, free hydroxide ions floating around in the solution. So the ability to do that makes something a base. Here's an example actually of ammonia. It's a weak base, as we'll talk about. And ammonia here will actually accept an H plus from the water. And in this case, it will make NH4 plus and it will make OH minus in this case. And again, that is a base because it has the ability to produce OH minus. That is a weak base because it's got to go do a little reaction with water to kind of produce that hydroxide. You might also notice it is kind of reversible arrows happening there, like a weak electrolyte, as opposed to a strong acid or a strong base is a strong electrolyte. Now, if you took something that is a strong base like sodium hydroxide, when that is in solution, it is again going to 100% break apart into its ions. It will not stay together, and you're going to have 100% of this. That is why if you took sodium hydroxide and you put it sort of in a solution, or you had a solution of sodium hydroxide, you will create Na plus and OH minus, for example. But this OH minus production is a lot really, really quickly because all it has to do basically, because it's a strong electrolyte, is go for a swim. It has the OH with it. It's just going to release it basically. And that makes something like sodium hydroxide a strong base because it can just release a lot of OH minus really quickly. NH3 here is a weak base because, like I said earlier, it has to kind of do a little work there to produce the hydroxide. It's not like carrying the hydroxide with it. So it's got to kind of do a little bit of work to produce hydroxide. So it's not going to produce anywhere near the amount of hydroxide in solution of something like sodium hydroxide, again, which is a strong base in this case. A lot of our strong bases come from group 1 and group 2 on the periodic table. The word group 1 is the alkali metals. Group 2 is the alkaline earth metals. The word alkaline means basic. So a lot of people from group 1 and group 2 on the periodic table that has hydroxide in the formula, like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. That's where a lot of our strong bases come from, kind of group 1 and group 2 in the periodic table that has hydroxide sort of in it. I will say that a lot of weak bases, as we'll talk a little bit about, as you might see as well in this chapter, a lot of weak bases are really organic sort of bases, and they usually will have nitrogen, very similar to NH3. They may have some carbons and hydrogens with it, but they usually a lot of times will contain like a nitrogen and a hydrogen in there. And a lot of weak bases are sort of organic sort of compounds. Yeah. Yeah, so I think your question is do is there like a shorthand for this equation like there is for like you could do up here type of thing? And the answer is usually no. Really for bases, so I would say this for acids, most people a lot of times when they're just showing the acid basically breaking apart in sort of water or just solution, will oftentimes do it this way where they just show the H plus comes off. And for the base, though, it is actually pretty good idea if it is not a strong base to show the water in the equation. And because a lot of times people struggle with, especially with later on this chapter, we'll talk about writing equations, or you'll need to write equations for some weak bases. Sometimes people struggle to try to figure out like where the hydroxide comes from because there's no OH on like the NH3 or anything like that. So my recommendation is definitely if it's like a weak base, I would actually include the water in the equation. That way you could kind of visually see perhaps where the hydroxide comes from. Um, but there is kind of no shortcut. I mean, there is, but most people wouldn't necessarily write it. But the shortcut would be not putting the water in there. And again, just basically just taking the water out is kind of the shortcut that you would sort of end up with in this particular case. So most people won't really write it like that. I would include the water for something that's weak. Other questions? Okay. Now, that was a good definition of an acid and base, but it was limited because he did a lot of work with hydroxide bases or bases that had hydroxide. And as we just saw there, not all bases will actually have hydroxide on it. So a more general definition of an acid and base is the Bronsted-Lowry definition of an acid and base. And the Bronsted-Lowry definition of an acid is a proton donor. So when we talk about a proton, we're talking about an H plus. The reason, again, H plus is referred to as a proton is because hopefully you remember hydrogen has a proton and an electron. Hydrogen does not have a neutron, right? So the element without a neutron. So the way you become positively charged is you have to lose an electron. So when that happens, H plus, the hydrogen is left with just a proton. So it is sometimes referred to as a proton in acid-base chemistry. And a Bronsted-Lowry base is something that will accept it. The H plus is actually really important here because people get the H part of it, but the positive charge there is also really important because if you lose something that is positively charged, so if you lose an H plus, you're going to become one more negative, right? You basically lost their proton, so now you got like more electrons, right? So you can kind of become more negative. And if you gain a proton, you're going to become one more positive. So it's really important. The sign of things does change as somebody gains or loses an electron, or I'm sorry, a proton. So in this particular case, NH3 is our base, as I mentioned before. Water here is going to act as our acid, and that means water is going to send the proton over to the other side. When it does so, it will create on this side NH4 plus and OH minus. And now the consequence of the Bronsted-Lowry definition is it will actually create what are referred to as conjugate acid-base pair partners. So they'll kind of create partners on the other side that's related to each other. So the NH3 on this side is related to the NH4 plus on the other side, and that is what is known as the conjugate acid. And the acid on this side, the left-hand side, is related to the guy on the other side, which is known as his conjugate base. So these are partners to each other, and the absolutely positively only difference that you could have in order for something to be sort of a Bronsted-Lowry conjugate acid-base pair is this guy right here. It is a 1 H plus difference is the only thing that there can be. So if you look here from the base to the conjugate acid, it has one more H plus because it picked it up. And as you go from the acid to the conjugate base, it has one less H plus, which is the one that's traveled. So as I mentioned a second ago, when the water loses the H plus in this case, it goes from a neutral state to one more negative, and that is how we get to OH minus in this case. When the NH3 gains the H plus here, it started neutral, but it gained an H plus, so it then gains a positive charge. So as I was mentioning before, the charges do change as that H plus is being transferred, and it's really important to sort of recognize that. Any questions on that there? By the way, we could also look at our acid dissociation that we saw on the previous slide with the water. And this again is going to give us H3O plus and Cl minus. Now, in this particular case, hydrochloric acid is going to be our acid. Water is actually going to act as a base in this case. And in this particular case, what we're going to see is it's going to be the acid sending DH plus over. The result of that, again, is going to make our H3O plus, and then they're going to be left with Cl minus. So the acid on this side is related to our conjugate base over here. And our base on this side is related to our conjugate acid on that side. Now, when you're talking about just regular old acid and bases, always left-hand side of the arrow. Conjugate acids, conjugate bases, right-hand side of the arrow is typically where you find those guys on the product side. You may also be looking at water and going, how come in one case it acted as an acid, and in one case it acted as a base. And that does happen with different substances, and water is an example of that. That is what is known as an amphoteric substance. It is a substance that can act as an acid or a base. And water is an example of that, as we will see shortly as well. Typically, things that have a hydrogen and a negative charge can do both things, can act as an acid or base, like bicarbonate or something like that, or bisulfate. Those guys, because they have the hydrogen to give, they could give it, and they could also accept it along the way. Any questions on that there? Yeah. Top left, an amphoteric substance. Amphoteric substance is a substance that can act as an acid or a base. Yeah. It, there are other ones. So, water is an example who could do that. And honestly, anything that a lot of times that have a hydrogen and like a negative charge can do it, like HCO3 minus, HSO4 minus. So these things, because they have a hydrogen, and like I said, they can sort of donate. But with that negative charge, they also have a spot for it, because the only way to become that negative charge for these guys is to lose the hydrogen. So they have a place to accept the hydrogen as well. So it can kind of go both ways. So anything that's kind of derived from a diprotic acid, something that has two hydrogens give, the kind of middle guy usually can kind of go both ways and act either as an acid or a base. Other questions? All right. So why don't you take a moment here, and for each of these, try to determine which one of these are conjugate acid base pairs. So take a moment, see if any of these pairings are. Okay, let's take a look. So hopefully what you are looking for, if you're not sure, is this basically. So once again, in order for these things to be sort of Bronsted-Lowry sort of conjugate pairs, that should be the only difference that there is. So if we take a look at the first one here, we got HCl and OCl minus. That is an H plus difference, but it is also a difference of an oxygen, right? So one has oxygen, one does not. So because of that, that will not be pairs, because the difference is obviously more than just the H plus. We take a look at the H2SO4 and the SO42 minus. Difference between these guys is it's actually two H plus difference, right? Would that make them pairs? It actually would not make them pairs. So they are not pairs, even though they are related to each other. But they are not related to each other in terms of the Bronsted-Lowry definition of pairs. Here we take a look at NH4 plus and NH3, and the difference here is one H plus only, right? So that looks like a winner at least, yeah. Lastly there we got H3O plus and OH minus. Difference here is two H pluses, yeah. I can do my math in my head. It was a lot of math there. So that's two H pluses, right? So are they pairs? They are not pairs either. Obviously, we had one pair there, which was number three, is the only pair that there is. Any questions on that? Now, the question may be, aren't these things related to each other? And the answer is they are related to each other, but they are not related to each other, like I said, as sort of Bronsted-Lowry conjugate base pairs. H2SO4 is a strong acid. It is also a diprotic acid, which means it has two hydrogens to give, right? So you have something like HCl, which is a monoprotic acid, which means it's got like one hydrogen to give. You have something like H2SO4, which is a diprotic acid. It has two hydrogens to give. And by the way, if you have something like, say, phosphoric acid, that's a triprotic acid, and it's got three hydrogens to give. Now, what you may have learned maybe in Chem 50 or maybe saw in Chem 50 if you did see H2SO4 is sometimes it does appear that those hydrogens are just going to all drop off at once, basically, right? So you probably like wrote it and then like both hydrogens are coming off and all that. What actually does happen when you have multiple hydrogens that come off with a diprotic acid or a triprotic acid is it actually comes off one hydrogen at a time. So something like sulfuric acid, the very first thing that's going to happen is it is just going to drop off one hydrogen only and make some bisulfate here. And then the second step that's going to happen is the bisulfate that's already lost the hydrogen will then lose a second hydrogen and will make sulfate in this case. And that is why if you look at this, H2SO4 and HSO4 minus are partners. The only difference there is one H plus. HSO4 minus and SO4 2 minus are also partners because again the difference there is one H plus. But if you try to go directly there, they are not partners because again that difference is two H pluses down the road, even though they are related to each other, but they're not related to each other in the sense of Bronsted-Lowry. Any questions on that there? Now, if you add these equations together, this is probably how you normally have seen maybe sulfuric acid is this guy will cancel, and then you end up with the overall reaction, which is typically what you look at in something like Chem 50, and you got two hydrogens coming off and a sulfate, right? So you look at that as the dissociation. That's really the overall reaction that's happening, but it does happen in a stepwise fashion when there's multiple hydrogens that come off. Any questions on that there? All right, so for this one, we want the conjugate acid for C6H5NH2. So what is the formula of the conjugate acid? Hopefully it's up there somewhere. Okay, so let's take a look at it. And again, understanding the sort of Bronsted-Lowry relationship can help you with this. So remember, we have a acid and a base on the left-hand side of the arrow. Then we got some conjugate partners on the other side, our conjugate base and our conjugate acid. And again, the relationship there, as we talked about, is the acid on one side is related to the conjugate base on the other, and the base on one side is related to the conjugate acid on the other. So if you come across a problem that isn't as nice as this problem, most of them are not, and they just ask you to write, say, the conjugate acid or write the conjugate base, and they don't really tell you, what that thing is you're looking at. You can use this relationship to sort of figure it out. So the idea here is we're looking for the conjugate acid, so that is here. I'm looking to end up over here. So if I just follow that back, what I am looking at is a base. And what I have to do at this point is just use the Bronsted-Lowry definition of a base, which is it should accept an H plus, right? Or if it was an acid, it should donate an H plus, right? So this helps you sort of decide, should you put the H plus on or should you take the H plus off? And again, if you kind of think about it sort of backwards of where it came from, it could kind of help you. So in this case, we are going to assume, obviously, this is a base. It's going to accept the H plus, which means we just need to simply put an H plus on that. I'm going to put my H at the very end. So instead of 2, I'll have 3. And remember, it's not just an H. It is a plus. So that thing was neutral to begin with. So now it should be positively charged. So that looks like number 2 there, I think, if I'm not mistaken. Any questions on that there? So if we had something like HCO3 minus, what would be the conjugate acid for that? And what would be the formula of the conjugate base? In each case, you are starting with this guy. So write the formulas for each of those. Okay, so again, when we're doing this, it's all about the H plus, either going to put it on or take it off. So we'll start with the conjugate base. So again, just thinking about it backwards, if I want to end up at the conjugate base going backwards, that means what I'm looking at in this case is going to act as an acid. And again, the definition of an acid is to donate the H plus. So as we go from here to here, it's going to get rid of an H plus, and we should end up with a CO3. I lose a positive, I become one more negative. I already started at -1. So now I become -2 there and become carbonate in this case. Yeah. Any questions on that? Conjugate acid, just like in the problem, if I want to end up at my conjugate acid going backwards, I see in this case, this guy's going to act as a base, which is going to accept the H plus. So as we go from here to here, we're going to add that H plus in. So that gives me two H's and a CO3 plus 1 and -1 equals 0. So it becomes neutral and it becomes carbonate in this case. Another example of a substance, as we talked about earlier, that can basically be amphoteric, can act as an acid or a base. Why would you not do this? So really, in this case, we're really just looking for its partner on the other side. And its partner in terms of the Bronsted-Lowry definition will only be a difference of an H plus. So when you're doing something like this, it's not necessarily you're writing an equation or anything like that. So what you're looking for is its partner that the H plus is the only difference that there should be. So either you're going to want to put it on or put it off in this case. Yeah. Other questions? And in this case, for example, in this case, it could be the water that's accepting the H plus, right? Or it could be the water maybe that's donating the H plus in. And if that helps you, you can. But ultimately, what the question is really looking for is just the end result on the other side of its partner, basically. Other questions? All right. So obviously, you need to be able to write Bronsted-Lowry acids and bases. Let's talk a little bit about water and the autoionization of water. Water, as we talked about, can act obviously as an acid or a base. And it can even react with itself, where one water is acting as an acid, the other one is acting as the base. And frankly, that is what is going on in water at all times. So here we have our acid and our base occurring here, and our conjugate pairs happening in this particular case. Obviously, if this is the acid, it's going to send the H plus over, and that is going to generate our H3O plus on the other side, and also our OH minus on the other side as well. So again, our acid and conjugate base, and these two guys partnering up in this particular case. That is, dare I say, an equilibrium, which is our favorite thing in this class. So you can write an equilibrium constant expression for this reaction, basically of water with water. And we could go K is going to equal our products, which is our H plus times our OH minus. We will not include the water here because it is a liquid in this case. And oddly enough, or strangely enough, this is a K value known as Kw for water. Yes. So this actually does equal an actual number of 1 times 10 to the minus 14 at 25 degrees Celsius. Now, as you can see, we could also represent in this case basically water reacting with the water. And you could write the same expression over here, Kw is equal to H3O plus NOH minus, and that will equal 1 times 10 to the minus 14. So earlier, like I was talking about, you could substitute out, again, H plus or H3O plus, again, meaning the same thing in this particular case. Any questions on that? So as I mentioned before, this is actually a value of 1 times 10 to the minus 14. That's at 25 degrees. And I would say for the most part, you could kind of assume that's going to be a constant value and probably the value that you're always going to use in most cases. But something you should remember is obviously it is a equilibrium constant expression, right? And one thing that affects the value of the equilibrium constant is what? Temperature. Yeah. So if it happens not to be 25 degrees Celsius, your Kw value may actually be a different number than 1 times 10 to the minus 14. I would say a very rare case that would probably occur. If it does occur, like in a homework problem or something like that, either in the problem, they will give you the KW for that temperature or refer you to like a table to look it up for that temperature. Other than that, probably 99.99% of the time, you can roll with 1 times 10 to the minus 14 and you'll be in good shape. But again, if you happen to see it's not technically 25 degrees or the problem specifically states a different temperature, you might want to keep that in mind. They may want you to use a different value for KW because it does change with temperature. But again, probably almost 100% of the time, 1 times 10 to the minus 14 is good. Now, what can we use this for? Well, really, again, the H plus part here is the acid part, and that is the base part of the solution. So we could compare the concentration. And again, a reminder that when you see those brackets, that is concentration, right? And again, that is molarity that we were talking about. And the good news is if you have one of the concentrations, you could solve for the other by taking 1 times 10 to the minus 14 divided by the other concentration. It really is the same calculation, regardless of which one you are solving for in this particular case. Now you can compare the H plus concentration to the OH minus concentration, which is basically comparing the acid part of the solution to the base part of the solution. And if they are equal to each other, they both will equal 1 times 10 to the minus 7 molar, and you will have a neutral solution. So if you have an equal amount of H plus and OH minus, your solution will be neutral. If you compare the H plus concentration and it's larger than the OH minus concentration, basically means you have more acid than base in that solution. It's going to be an acidic solution. And if you compare the OH minus is greater concentration than the H plus concentration, then it's going to be a basic solution. The relationship between H plus and OH minus is an opposite relationship, which means as the H plus concentration goes up, the OH minus concentration goes down. So they run opposites of each other. And obviously, as the H plus concentration goes down, you will see an increase in the OH minus concentration. So they do go opposites of each other. So if you have a really big H plus concentration, you're going to have a really small OH minus concentration. And that's why your solution is going to be pretty acidic at that point, right? And vice versa, if you have a greater OH minus floating around in that solution freely, then you do H plus, you're going to have a much more basic solution because you have a lot more of the hydroxide basically floating around in that solution. Definitely, when you're doing these calculations, you want to definitely make sure that you're using your exponent button, or you're going to be in a world of hurt on your answers in this chapter for sure. So make sure you are using that E button, the EXP button, and your exponent button when you're doing that. So why don't we try one here? What is the concentration of hydroxide in a hydrochloric acid solution that is 1.3 molar in hydrogen ions? So take a look at it since we're getting to the end here. Obviously, here we could use our KW, which again, you should think of it as something you always have sort of available to you if you need to calculate some type of concentration. And again, as I mentioned before, you can use H3O plus instead of H plus if you want to. In this particular case, we are looking for the hydroxide concentration. We are given the H plus concentration, 1.3 molar. So rearranging that equation and solving for hydroxide, 1 times 10 to the minus 14 divided by our H plus concentration, popping in our numbers there, and a 1.3. That's going to get us there. Looks like 7.7 times 10 to the minus 15 molar in this case. By the way, that is a concentration and it does need some units, yeah, like molarity. At this point, we can then compare our H plus concentration to our OH minus concentration and see which one is larger. And in this particular case, the H plus is definitely larger. And because it is larger in this case, when we compare these two numbers, this would tell us this is obviously an acidic solution, which we would hope since it's a hydrochloric acid solution. So that sort of makes sense, right? It would be bad if it was a basic solution at this point. Yeah. Any questions on that there? All right, let's lay that up.